Hi everyone. Today I will be talking about magnetic force and field. So this is chapter 29. And what is a magnetic field? I will give a brief overview, then focus on the right-hand rule, which is to find the direction of both the magnetic field and the magnetic force. Okay, so the magnetic field of a magnet. A magnet has a north end and a south end, like here. It's very similar to how an electric field or like a battery has a positive end and a negative end. And we know that similar charges repel and um, different charges, like opposite charges, attract. So this works the same for the magnetic field. As you can see here, the when we have a north pole and this north pole, it will repel each other. As you can see from the magnetic field lines, that it's going away from each other. Just like how when we have like a negative charge and a negative charge, its electric field lines are the same. However, if we have different opposites, I guess, poles, like the North Pole and the South Pole, they actually attract each other, as you can see from the magnetic field lines. And it's very similar to the electric field. Yeah. So this is one example. A real life application example is the compass. The compass has a north end and also a south end. And as you can see, these particles are kind of like the direction when the compass points you to like the north or the south. So it works the same. This red part signifies like the north end of the particle, and it will repel this north end. Therefore, if we had like a compass like this, or this north end and this north end, it would actually turn directions and attract the south pole. So if so, this North Pole and this North Pole, it just emphasizes on the fact that they repel, and this North Pole of this particle will always attract the South Pole. As you can see, this direction of these particles. Yeah. Another example is the magnetic field of Earth. Earth serves as like a big magnet in itself, where this is like the North Pole and this is the South Pole. That's why we have like North Pole and South Poles. The axis of rotation for this case is this axis of Earth, and the particles always travel from the north to the south, like this. Just like in a battery, the particles go from the positive terminal to this negative terminal in like a current. Yeah. I mean battery circuit. Yeah. Now I will be talking about how to calculate a magnetic field of a current, which is probably like the easiest and most simplest case right now. So B represents the magnetic field, and this is the general formula, um, where mu zero and 2 pi are both constants, and I represents the current of your magnetic field, and which is this line right here, and R represents the radius in which, like in the circle. So it could be like this radius or like this radius, depending on which like magnetic field you're you're calculating. Yeah. So be sure to remember this formula. And this is just the, I guess, what the constant mu zero is. You can memorize it or it's just not necessary. Now we will talk about how to find the direction of the magnetic field of a current. So here you'll need to use the right-hand rule. So the first case of the right-hand rule is, I will open my camera to show you. So the first case is that As you can see from this, you would first point your thumb to where to the direction that the current is in, and then you would take these four fingers and then kind of tuck it in, and now this will be the direction of your magnetic field. Just step one, point your thumb to the current's direction, and then open your, I guess, fist, and then open your palm and these four fingers, tuck it in. And now this is direction of your magnetic field. Yeah. So that's it. That's for the magnetic field. And then now we will talk about the magnetic force, which is represented by F. And these are the two, I guess, most important equations for the magnetic force of a current. These two essentially mean the same thing. So this is cross multiplication. The expanded version of this is magnitude of QV times the magnitude of B, and then times a sine theta or alpha. It doesn't matter, but this theta, remember, is the smallest angle between your velocity vector and your magnetic field vector. So this angle would be like your theta. And make sure to take the smallest one because there's like the small angle and the big angle. Yeah. And the unit for magnetic field is 1 Tesla. Yeah. So this is the formula for magnetic force. Q represents the charge, V represents velocity, and B represents the magnetic field. V and B are both vectors, therefore F will be a vector, and Q is, I guess, just a scalar value of your charge. Yeah. So now that we can find the magnitude of magnetic force, now we'll use the right-hand rule again to find the direction. Yeah. So how to find the direction of the magnetic field, magnetic force, we'll use the vector of magnetic fields and also the velocity vector. So this time, I'm gonna open my camera again. Yeah. So this time, as you can see, let's take an example for this. You can take this one as an example. So first step is in this question, we will most likely be given the direction of V and direction of B. We will need to find the direction of F. First step is to point your hand in the direction of B. For example, just since like the V is pointing, I guess, outside of you, so just put your hands like here. And then, as we talked about before, this angle is your theta, and using that angle, and the hand, like the V, we can see the vector B is over there. So use these four fingers and curl it up in the direction of B. So maybe something like this, because your V is pointing like here, and your B is on top of V. So it would like curl on top. And then as you can see, my thumb is now pointing to the right side. And I guess that would just be your vector of force, magnetic force, like this. Let's try another example. So this one. Always remember that your four fingers curl up in the direction of B, but using this smaller angle. Yeah. So as you can see, there's like a big angle here and this small angle here. Curl up using these small angles. Yeah. So this time again, I don't know if it's gonna curl up or down, but I guess B is still like this way, but you can see that B is actually going like here, so I can't do that. I'm gonna flip my hands kind of like this so that these four fingers can easily just curl inward towards me. As you can see, V, your hand, first step points to V, second step curl in the direction of B, and wherever your thumb is pointing will be your magnetic direction of magnetic force. So pointing down, therefore your magnetic force is going down at this angle. Yeah. This third example, you can feel free to try it yourself. It could be like a practice exercise. Yeah. So now I will just recap of what I talked about today. First of all, there's the magnetic field. Um, Remember the direction of the North Pole and South Pole. And to make it easier, just relate it to like the electric field. It's essentially the same thing. Think of the North Pole as the positive terminal of the battery and South Pole as the negative terminal of the battery, or like vice versa. Yeah. But always remember that the direction of magnetic field is always from North Pole to the South Pole, and just like the circuit. And these are two examples of applications of magnetic fields in like real life. Pretty cool. And now we talked about the magnetic field of a current, the most simplest basic example, the magnitude, and using the right hand rule to find the direction. And then the magnetic force of a current, or like honestly anything. This is a more like general formula. Once again, this is like the derived version, like expanded version of the magnitude of magnetic force, and use the right hand rule once again to determine the direction of magnetic force. Yeah, and all of these pictures and text I took from the AP Barron, I think, just AP Calculus book. I will um, attach like a PDF, a little bit of PDF version down below. So feel free to read chapter 29 again and stay tuned for more videos of more applications like the Gauss law for magnetic field, Ampere's law. And this is just a little introduction in basic for magnetic fields. Thank you so much. See you guys next time.